Hello, good afternoon. Here at the fourth session of the E-flight-expo here at AERO 2025. And we're talking about something which makes a difference between conventional aircraft and electric aircraft, which is the electric propulsion system. So with this, I give the word to you, David.
All right, thank you, Willi. Thank you for inviting us back to the stage. I'm David Eichstedtt. I am VP of Product Management at Verdego AERO. Just a quick little background on Verdego. We are, as Willi said, we are focused on hybrid electric power plants. We have about 35 employees, and we are located in Daytona Beach, Florida, in the research park that's affiliated with Embry-Riddle Aeronautical University. My background, I have engineering and program management background. Verdego has been around for almost 8 years, since 2017, and I was the first full-time employee hired in 2019. So I've seen a fair amount of growth in the company over the last 6 years. It's been an exciting team to be with. So let me start out with just a little introductory video.
The VH4T turbine hybrid power plant is the highest performance system on the market right now. Using the Pratt & Whitney turbine and Verdego's proprietary hybridization technologies that are built around it, we've got a new type of power plant that delivers onboard propulsive electricity at 800 volts DC and 400 kilowatts continuous power output. You can think about replacing the huge battery pack with this 550-pound, 400 kilowatt power generation system, a much smaller battery pack, and a fuel tank of either jet fuel or sustainable aviation fuel. And what that gets you is up to 10 times the range, higher cruise speed, and more payload. There are a lot of missions where the military needs to go very long range, and they need to go all the way out and come all the way back. Let's say an urban air mobility aircraft. You may be able to take that range up by a factor of 10 while also taking the cruise speed up by 20 to 30% and taking the payload up. We're powering the electric flight revolution, so we can use these next generation liquid fuels, run them through the VH4T, and power the electric motors in a next generation aircraft and get all of the benefits of the two most exciting revolutions in sustainable aviation. Hybrid electric is going to be the right solution that gets us the next generation of aircraft that are more efficient, lower cost, longer range, higher performance, and safer.
All right, so it has been 2 years since we've spoken here at AERO. Last year, the schedule didn't permit, so this means you'll get not just a 1-year update, but a 2-year update on things that have been happening at Verdego. Things have been moving fast. Our VH2 unit, which is a custom system for a specific customer, we've delivered multiple copies of that piston hybrid system, which are now installed in a customer aircraft, manned aircraft in flight test. So that means we've achieved TRL-7 with our piston hybrid architecture. The turbine test stand you see in the lower left corner was an Ironbird system to get us started into turbine systems. So since the last time we were here, we built that, which then led us to the VH4T, which you just saw in the video. Which we have built and done some significant testing, and we're having a very strong positive market reaction to this product at this point. Since that time, we've generated 1.3 billion in LOIs for our power plants, so we are getting a significant amount of interest. And both the VH3 and the VH4T are now progressing into the production versions, the conformal versions that we will take forward to Part 33 certification. So I want to share a little bit about Verdego's technical and business approach, where we stand in the value chain. So if you look at an electric powertrain for an electric aircraft, you can divide the powertrain into an upstream and a downstream segment. The downstream is the section that has the electric motors that drive the lift rotors, the lift propellers, the lift fans. It's where the power is consumed on the aircraft. And these components are all highly customized to each specific aircraft that they're designed for. On the other side, you have the upstream components. This is where the power is generated or where the energy comes from. This is a section that we play in specifically with hybrid power plants, but other elements that can be in that part of the system would be, of course, batteries, hydrogen fuel cells. On the upstream side, we see the potential for having a lot of commonality across multiple different aircraft platforms that have similar overall power requirements, which makes for maybe a slightly easier business model with not so much of a mix and a little bit more volume. From a business standpoint, what Verdego does is we are a power plant company, but we are not an engine company. So we do not develop our own engines. We like to start with engines that have already been developed and certified, whether they are piston hybrid or piston systems or turbine systems. To those existing engines, we add all the components to turn it into a hybrid power plant to generate both electricity and mechanical shaft power output. So that means there's the engine core, we add generator, inverter, all the physical, mechanical integration of those components, the control system that also communicates with the flight control system, and the integrated thermal management system, which is kind of a core feature of Verdego's power plants. We intend them to be used in eVTOL aircraft, which may be sitting on the ground and might not have any airflow flowing over them. So in those conditions, we believe the power plants need to be able to cool themselves with no additional outside airflow. So from building the power plants, we sell them to the aircraft manufacturers as a Part 33 certified product, which they can then install in their aircraft. Aircraft manufacturers then, of course, pass them along to the aircraft operators. It's interesting in this industry, there are some people who participate in all segments of the value chain. They're doing everything all themselves. That's not Verdego. Our focus is the hybrid power plants. So let me get into some of the details about the power plants themselves that we are working on. So the VH3 is the first one that we started working toward. This is the one where the predecessor has already been flying in the customer aircraft I mentioned earlier. So this system, it's a piston system using an EASA certified compression ignition engine, which means it's a diesel cycle. It's the SMA SR305, a special version of that one that's made specifically for us to ease the hybridization element of it. It puts out 185 kilowatts of continuous power, which can be either electrical output, mechanical shaft output, or a combination of those two types of power. It does weigh 295 kilograms, which gives it a low power density, but what that buys you is a very efficient system. The specific fuel consumption is very low at 227 grams per kilowatt hour, and that is a measured number, that's not a calculated number. The FAA certification on this is in process. We've been working with the FAA pretty closely for about 4 years now, and the approach we're taking is Part 33 plus special condition, because the Part 33 elements cover the thermal engine quite well, but then there are all these hybrid elements that come in that are kind of outside the normal FAA realm. So you put these two together and you end up with an engine certification project. Types of aircraft that this can go into a range of different kinds of aircraft. Of course, eVTOL is our primary target, whether that's a manned air taxi application or say maybe a cargo drone. The power level from the VH3 is suitable for something in the around 200 to 250 kilogram range of payload. But due to the efficiency of the system, it's a great solution for when you need long endurance, long range applications, or if your focus is on lower fuel burn for direct operating cost and as well as lower emissions. As far as the status goes right now, we have an Air Force contract. It's a TACFI contract that is developing the first conformal prototype. And we expect that to, the first engine run on that product to be in the fall of next year, probably in the September or October time frame. So that's the VH3. Next is the VH14. So this turbine hybrid system is built around a Pratt & Whitney PW206 or 207 engine. That's a helicopter engine, the one that's used in the Augusta A109. I should mention here that Verdego's lead investor in our, so far our largest shareholder in the company, is RTX Ventures, who is the parent company of Raytheon, who owns Pratt & Whitney, which gives us a good solid relationship with both Pratt & Whitney Canada and the guys in Connecticut. So this system puts out roughly 400 kilowatts. The R&D version that you see here and that was in the video is a 375 kilowatt system. Looking ahead, the production version will put out more power. It'll be about 415 kilowatts. The R&D version weighs 511 pounds. In production, it'll be about 550 pounds. And this one also will be available to drive both series and parallel output. So I'd like to talk through a little bit of some of the math, just a representation of what was mentioned in the video. If you're looking at converting an existing battery electric aircraft, what does hybridization do for you? Well, in an existing aircraft, for instance, it has about a 2,000 pound battery, which is a little over 900 kilograms. If we convert that into hybrid electric, and again, that 900 kilograms represents the upstream powertrain component. If we build up a hybrid system, that battery shrinks down to about 1/10 the size, so about 90 kilograms. You get about a 250 kilogram power plant, marry that with 250 kilograms of fuel, and now you have, what was it, I think 581 is what the total was for, in kilograms for the total powertrain, which buys you a lot of extra payload, about 1,300 pounds, or what was the number? I lost track of the math. I think it was like 600 or so kilograms. In any case, this is a great solution. It gives you a lot more range, gives you the potential for more speed while increasing the payload capability. So this system, we've done some durability testing under an Air Force contract, again, U.S. Air Force. We simulated the Part 33 durability testing routine. So we had a representative mission profile. It wasn't just a smooth profile, it also featured some transients in there to deal with turbulence and so on. And we ran through that for 150 hours. Came through in flying colors. Our production version, we're working on that right now. We expect it to have the first engine run in the first half of next year. But we're having an incredible positive reaction to the market on this system, because 400 kilowatts is just about the right amount for a lot of the 4 to 6 person air taxis that you see out there. So it's well sized for that application. As a result, we're starting to line up our initial production for selling some of the R&D systems, which are not going to take forward into production, but they're very good for conducting research and development. In fact, we now have systems available for not only for purchase, but for lease if you need to get into some early testing, ground-based testing for Ironbird systems and the like. So this is just a slide to quickly remind of what are the basic benefits of hybrid power plants. Verdego has some core capabilities in conceptual aircraft design. And so over the last year, actually, we've done quite a few studies on what the benefits are of applying hybridization to different aircraft configurations. And so in general, what we find is it's, you end up with an aircraft, if you go from conventional to like a helicopter to a different configuration that's hybrid, you tend to reduce the fuel consumption and the emissions significantly. You get higher speed, longer range, and increased payload. Now, these benefits are coming primarily as a combination of the hybrid power plus an airframe that is more efficient in cruise, has a better L/D in cruise than, say, a traditional helicopter. And it's the combination of those two that tends to create these kind of magic results. The last system I want to talk about is very unique. We call it the VH5 blended turbofan. This is a system that we came up with and then applied to an Air Force program called the HS VTOL Challenge. This is, it's kind of a unique engine. It's an electrically convertible engine that can, in one flight mode, produce massive amounts of electricity for vertical takeoff operations and hover flight, or then transition over to turbofan thrust, so you can get up to true high-speed cruise. Mach 0.8, Mach 0.9. If you had the right configuration, you could go supersonic if you wanted to. You can also blend those two, the blended output of electrical power and direct turbojet thrust. So if you're not using all the power from the turbine to go at high speed, if you back off on the speed a little bit, that extra power coming from the engine can be converted into electricity to help power the onboard electronic systems. And of course, that's of much interest to the military. You can see the different flight modes, how this works in the lower right-hand corner of the slide. With pure electric power coming out for the vertical takeoff. There's a transition where you're blending in between, and then finally getting into a forward flight mode where you don't have any electricity coming out and it's all going into thrust. So the primary applications for this, the first one was the HS VTOL mission I've just described, but there is potential for other aircraft that simply have needs for significant electric power on board. These could be things like collaborative combat aircraft, loyal wingmen kinds of projects. On the commercial side, think about what this could enable. Something like a vertical takeoff and landing business jet, so that the executives now can fly from helipad to helipad across long distances and high speed without having to transit through local airports. All right, so that's all I have to share here today. I just wanted to say that we've seen over the last 2 years the industry has shifted focus quite a bit toward hybrid power plants from the pure battery electric environment that it was a couple of years ago. And I just want to say Verdego has been working, as you can see, for a number of years to be prepared for this time. So we are ready with the power plants to help these new aircraft meet their very demanding mission requirements and mission goals. Thank you.
Thank you. Sorry, we've been a little bit long now, so I hope that we still have some time for a discussion, but if we don't, we all stay around here. If you have questions later, you can ask the questions directly. Our next speaker would be Theion, David Schaub from Theion. He's CTO of the battery company, and we've had them here a while ago, and Number 2. So, stage is yours.
Thank you so much. I think it's working, right? Oh, yes. So, thanks for the invitation. For me, it's the first time that I speak on an aviation congress like this in Germany. I've done it several times in China. And as already said, my name is Martin. I'm the CTO of Theion. And what are we doing at Theion? We are building crystal batteries for a carbon neutral future. And to give an insight what we are doing, electric flight is not longer science fiction. So when we have a look here, the things are really flying. It's also getting now closer to be commercialized maybe in the future. But one limiting factor, what everyone agrees on, is the battery. I brought one here, and what we are building are really lightweight batteries. Now, this is a representative for those who are interested in it. We have also a small booth here in A7. You can come and look at it. That's really a lightweight battery. I can also hand it to you. And the batteries are the limiting factor, or one of the limiting factors. Our mission is, from a market perspective, for sure, eVTOLs, where I need a lot of power, UAVs, but the current lithium-ion batteries are too heavy and partly also too weak. They do not generate enough power that you can go for the long distances and have enough space and backup to make also a safe landing later. Jet fuel has 50 times more energy per kg than lithium-ion, and also for sure you burn the fuel during the flight and the battery stays with that weight, right? It's not getting lighter. So we need better batteries and not incremental steps. So there's a lot of development going on, but we are talking more about an evolution, and what we are doing, we change the material of the batteries, and therefore it's more of evolution what we do. We are addressing a 20 billion euro market. Now the screen is gone. No problem. Just for you to have an understanding, the global battery market when it comes to electrical vehicles and also energy storage is much bigger, but it's even the aviation market is getting significant when it comes to batteries. The use cases here, why we are targeting, we can provide 5 times higher specific energy. Basically it means range extension. How we do that, you see here in the picture a small sneak preview how it looks inside our batteries. We are using sulfur as a material, so no metal, it's sulfur, it's very lightweight. And we use it in a crystalline form. So this is exactly how it looks. So this is so-called monoclinic gamma sulfur. It's sulfur we use with a very high porosity, because in our cell chemistry, lithium is going from anode to the cathode, so it needs room to lithiate. We have to give them room, and therefore we generate this monoclinic gamma sulfur phase, the crystal what we are using on cathode side. So here's some numbers. So we are focusing mainly on the cathode side. So cathode is the material that is more heavy in the actual battery. It's also the one that is the cost driver. So as an example that you can a little bit see what we can do, for cathode weight for 100 kilowatt hours, it's about, if you go for LFP, NMC, these are the most popular materials on the market. What you can buy with actual cell technology, you need 190 kg, 100 kg, and with sulfur you can go down to 41 kg. So it's the same capacity, but we only need 3 times of the weight. And that's not enough. The second beauty what we have is the cost. So at the moment, the kg of an LFP or NMC material is around 25 to 30 euros per kg, what you have to pay if you want to buy this material. And actually we are, as a very small company, we are buying the whole thing for about 8 cents per kg. So it's the performance what we can improve significantly, and also the cost perspective. To make it even better, the material challenge, maybe you heard, especially from the electrical vehicle market, that there's a huge challenge to supply this industry with raw material what they need. Some of them are quite critical to get, some of them are impossible to get for regional problems, and we don't need any of this limited material. So what we can also provide with the system is a supply chain independency from China. This makes us also quite interesting for regions and companies who can usually not participate in the battery market because they don't have access to the raw materials. So to summarize, we are using sulfur. Sulfur is already there, so it doesn't have to be mined for that. It's a byproduct of the oil industry. So we are really doing upcycling. It's abundantly available. So maybe remember when we had this acid rain in the 80s. So when let's say, when there was still sulfur in the fuel, what we are using for the cars. So now they have to take it out. The sulfur is there, so there are tons of sulfur everywhere in the world, and no one is using it. We can upcycle it. The energy density, 5 times higher in theory, when you just look at the molecules what we are using. The safety part is important. For sure, it's non-flammable. It's intrinsically safe. This means if we ram a nail through our battery, the sulfur is melting and it's closing the pores and it stops itself, so it's not exploding, but it's very nice. And I already mentioned some numbers about the affordability, let's say 20 cents per kg compared to 25 euros or 8 euros for LFP. So, who are we? We are quite small, 20 people, headquarters in Berlin. We have legal entities in the US, in the Middle East. What for us important is not only the technology, also that we can protect our technology, so we are quite busy with patents. We have 10 patents filed or granted along the complete process chain. And customer LOIs, supplier LOIs we are working on. And here you can see our nice building. What we moved in 2 years ago is some insights of our lab. So, if you are interested, you can contact us for sure over the homepage here, or I will be here today, A7, more or less directly in the middle. So, thank you so much.
Thank you very much, Martin, and sorry for mixing up your first name. And thanks for being quick. And I want to be quick as well. So our next speaker is working on batteries as well. And they are working on batteries, and they are from China, which was mentioned before, Professor Zhang. If you could give us an overview what your idea is for aviation batteries and where you are at your development. Thank you very much.
Thank you. Actually, I forgot your name. Martin actually gave a good, presentation on how important our battery is and how important to increase the energy density is for our electrical aviation, right? So today my presentation will be focused on the anode side. I think Martin have presented good potential cathode using sulfur. Well, everyone, if you know batteries, we are talking about lithium battery, lithium ion, we need a lithium ion. If you use sulfur, actually you need the anode to provide lithium, okay? So that means the lithium metal is needed. Eventually, that's the technology we have been developing since 2008. We started with lithium sulfur, and later we commercialized with we call the lithium metal battery. So because sulfur, we still have difficulty to make the commercialization. So we're still using high ternary oxide cathode. Okay, I'll do some explanation on why lithium is important. This slide, you see the history of our rechargeable batteries, okay? It's a long history. Some of our oldest lead acid batteries still in use, okay? Unbelievable. And now we are at the curve, very sharp increase of energy density based on lithium-ion battery technology. That means oxide, cathode, and graphite anode. All right, anode, cathode decide what the energy density of your battery is. Okay, so both are important. And in the future, we think they will reach their theoretical capacity. So there's no ways to increase energy density if you don't change your material. Okay, and here's what the batteries support for electrical aviation. I'll pass it. Everyone, I guess, know how important it is. Okay, and those different levels of application all requires good batteries. Not only electrical aviation, but also vehicles, also ferries, actually, in the future. Certainly our cell phone and every microphone, you need to charge batteries, okay? And the current status of lithium-ion battery, we can have energy density close to 330 watt-hour per kilogram. That can be reached by using an anode we call the silicon. Silicon combined with graphite. Okay, that's the status quo. And the next, what's next? Our next is lithium. Lithium is the lightest solid on Earth. Okay, if you want a good perfect anode, there's nothing can compare with lithium. Only lithium can provide your lightest anode material, period. Okay, so lithium is also reactive. That's why they can provide your electron, one lithium atom can provide one electron very easily. Okay, so they are compared to graphite. That actually is not a scientific comparison. Okay, but roughly you can see the number is already 10-folds of theoretical capacity. Okay, actually, if it's a fully discharged state, it's unlimited. Because if your cathode has lithium ion, you need your anode has lithium. That's why I have an infinite number over there. That's a scientific way to say it. Okay, just to let you know, lithium a possibility is limitless. Okay, so now you see at the top is status quo changed if we use lithium metal. We can reach above 500 kilowatt hour per kilogram. That's almost double than the conventional power battery we use in our EV. And those numbers actually is not in lab, not in research lab. It's in our product. We already had product. Customers are evaluating right now. I'll show some data. And lithium sulfur, maybe in the future we'll go to that area because we have been research on that for a long time, but next couple 5 or 10 years, we still stick on oxide-based cathode, probably. And you know, the lithium, the problem, I should go through very quickly. I think my time is very limited. Lithium metal is not new thing. Actually, the discovery of lithium ion, lithium metal was used for the Nobel laureates. All 2 of them using lithium metal as anode. But later, people find commercialization is difficult because dendrite growth can cause short and fire. So, saying that, people discovered graphite, carbon to replace lithium. But now the graphite reaches theoretical capacity. We have to use lithium, so we have to resolve this problem. Dendrite growth cause shooting. And one approach, people say, if you use solid electrolyte, block the lithium dendrite growth, penetrate the cell, you can have a safe cell. No, there's no magic like that. We find, academic community have searched a lot of solid state electrolyte. Until now, nothing can block dendrite. This is in my academic lab. We do this in situ characterization to see how dendrite grow through your solid electrolyte. Okay? Certainly, in the liquid, we can also use some technique we call the microcell. It's semiconductor industry trick. To fill this microcell with liquid electrolyte, we can also study how dendrite grows on top of lithium. And we found that, yes, if the video doesn't work very well, I don't think it's playing. Well, just look at the picture over there. Indeed, in traditional electrolyte, it grows very fast, like a minute, 60 micron. Our separator is now it's only 20 micron. So that means your cell will be short, less than 20 seconds. Okay? That's why lithium metal in conventional electrolyte, it doesn't work. So you have to change the electrolyte. Our change the electrolyte, you see, they can suppress the growth. Well, unfortunately, video doesn't work. We will have 2 different electrolytes. We can suppress the formation of dendrite. So don't let the dendrite grow is the solution we are looking for. And based on this research, we have developed different approach to suppress dendrite growth. Then we can make it commercial. Okay? I call it the back to the future because initially lithium-ion battery discovered we're using lithium metal anode. Now we coming back to lithium anode, but with a future technology to support it to be a safe chemistry. And that's our result. You see the video doesn't work. We realized this nail penetration lithium metal cell for the first time back in 2018. Okay, we did that nail penetration test. That means it's safe. But we also extended the cycle life to 600. Well, that's actually is an extreme condition in our lab. Actually, in practical condition, I'll show data. We recently collaborated with, I cannot disclose the name, but the eVTOL company. We collaborate with them using their flight profile. We can extend our cycle life at 1200, over 1200. That means it's practical now for eVTOL application, okay? So this is just a brief history of our company. And you can see 2008, we start working on lithium metal. And 2018, we have verified the safety. 2019, we have shipped the first batch of lithium metal battery with the energy density 420 watt-hour per kilogram. Now our energy density is 530 watt-hour per kilogram. Not only energy density, you know, for battery you need a balanced performance. For eVTOL, for example, you need a power, high discharge power, high current. Okay, for high power type, now we have 400 watt-hour per kilogram capacity, but with continuous charging capability of 15C. That means you can discharge like several minutes all your charge. Very high current, they support very high current. All right, that's the capacity, our production capacity. We can supply, right now we can supply up to 100 megawatt hour capability, production capability. We are expanding the production capability. And we have 3 series of products. High energy, that means we don't emphasize discharge power, and the high power type, and the other one is long cycle life. Well, long cycle life, actually now our P type, we just found our high power type can also support that. Okay, they have a different application scenario, but as I said, the balanced performance is critical for application. And in our support our electrical aviation, we try to work with various customers, drones, and high altitude platform, and this eVTOL. All 3 types we support. We have communicated with work with many customers. And this is just the result I mentioned recently. We have using a eVTOL profile provided by our customer and did the test. And our cycle before takeoff, flight, landing, this is 1 cycle. We tested we can reach, right now we can reach 1280 cycles. It's still going actually. The battery is still very well, very healthy. Okay, we did a healthy test, very healthy. We don't know how this can extend. If you go to 2,000 times, that means your eVTOL can fly to use the same pack of battery, can operate 2,000 takeoff and landing operation. All right. Okay, that's the most recent result I present for this conference.
Thank you. Thank you very much.
Later, I'll skip all this, everyone knows. I know my time is very limited, so I just say one word. It's in the next year, maybe our energy density will go to 600 because our lab is quite mature, but we'll have to work something out.
Okay, thank you. I think we are very, especially as you mentioned, 600. I think if you really keep your promise and you develop at the 600 next year or even 1 year later, I think everybody will be happy because this is really what we are looking for.
Okay, thank you very much.
Next, we go to a totally different subject because it's also about the energy which you need for flying. With the batteries now, we're not very happy. That's why there is also fuel cell. We had a whole conference on hydrogen and fuel cell in the first 2 days, on Tuesday and Wednesday. Karl from the High Flight project, Karl Käser, he will give us an overview on where they're working on, and we heard there's been some good progress recently. Thanks, Karl.
Okay. Good afternoon, ladies and gentlemen. Welcome to the presentation this year of the progress with the Hi-Fly H167 hydrogen fuel cell powertrain, which is taking off here in Germany. The advantages of the fuel cell system are obviously very easy. It has zero CO2 emission. It's a low noise system and it provides long range. The overview of our product you can see here. The H167 will deliver or is delivering 70 kilowatts of power for takeoff phases. So we can substitute the Rotax 912 engines and similar engines. With 7 kilograms of hydrogen on board, we have 5 times more energy at the same weight than a comparable battery solution. Yeah. We use automotive standard 700 bar, that's the same standard that is used by Toyota Mirai or Hyundai Nexo to keep the system comparable to what the rest of the hydrogen industry uses. Due to the modularity of the design, the system is configurable to various types of aircraft, not only winged aircraft, light sport aircraft or motor gliders, but also to eVTOL and UAV. In the last year we have completed our flight demonstrator, and I think this is the next slide, where I will show you the video of our first flight. Okay, when it comes to hydrogen-powered aircraft, one of the main topics is always the question about infrastructure, how to get hydrogen, how to come to refueling your aircraft. HiFly is working here with several partners on the equipment of airfield, and here you can already see maps on the map where you can refuel your aircraft. The market for our system is huge. Yeah? The target market for what we are developing now are light sport aircraft, light aircraft and ultralight aircraft, and motor gliders. In the future, we will extend the application also to light Part 23 aircraft. And the future market, of course, includes the future air mobility, the regional air mobility, and the UAV aircraft. HiFly has already two launching customers, one OEM for light sport aircraft and one startup company for eVTOL aircraft. We have letter of intent with several other light sport aircraft manufacturers, and we have consulting contracts with Part 23 companies. HiFly is an endeavor of the companies PS Hightech and Kasero. PS Hightech brings in this cooperation its expertise on hydrogen systems, hydrogen storage, and the spherical fuel tank, which you can also see at our booth. Kasero is a R&D company located in Stuttgart area, and we have a long tradition of certification work as well as manufacturing and design work for aviation and aviation components. So the milestones we have achieved so far, we have refurbished and retrofitted the testbed aircraft, which is a domain to a DS2C. So it's now the DS2C/High. We have won the Sustainable Aviation Award 2023 already here at AERO, and it was exhibited here 2024, and also in 2024 it was exhibited in the Green Tech Festival in Berlin. The first flight took place last year, and this year we are nominated for the Sustainable Aviation Award again in the category supplier. The next step will be market entry with the start of series production for these systems and certification with OEM in the ultralight category. Then the logical next step will be upscaling to Part 23 and regional air mobility. Thank you for your attention, and if you want to continue the discussion in person, you can visit us in the booth A7221, and you can contact me and the co-founder Peter Statthalter with the contact addresses that you see here. Thank you.
Thank you, Karl, very much. Karl has been here at the E-flight-expo, I think, since the beginning, with very different projects, and comes again and again, and he's having a lot of progress. They did win an award here also about 2 years ago, and now we have a company which is brand new here at the company. I have to admit, although I'm in the electric aviation quite for a while, I did not hear much from you in electric aviation before, but with this I pass the word to eMoSys. I want to announce you right. So it's Stefan Exi. No? So, okay, then you tell us, because that's what the information I received. So Ferdinand Wolf, Head of Finance, will present about eMoSys. You're working on motors, if I understand this right.
Yes, absolutely. Many thanks for the invitation. So my name is Ferdinand. I'm here representing eMoSys. We actually wanted to send our CEO, also our technical director did not find any time today. So I'm afraid you have to deal with a non-technician guy today. I kindly ask my colleagues here on stage to be gentle with me later in the discussion. Yeah, so my background actually is I've been in aviation for quite a while. I'm responsible for finance, IT, procurement, and as well as accompanying the business development part and respectively here today. Let me quickly introduce you to eMoSys. So unlike what we've heard on fuel cell systems, whole aircraft or batteries, we are really focused only on electric motors. The motor itself, as well as the inverter technology or the power electronics behind. We have been founded in 2013. We are actively in the marketing since 2018, initially with motorsports, which is the original, so not automotive standard, but rather high performance applications. And ever since 2023, we are 100% subsidiary of MTU Aero Engines, as you may know, certainly the leading aero engine manufacturer in Germany. Ever since, of course, our focus is strongly on aviation, and I'd like to guide you through a little bit of what we're doing now, what our technology is, and what sets us apart from competitors. Firstly, we have a quite small and dedicated team to a few areas, starting with pre-design. I'm going from simulation to mechanical engineering, electrical engineering, and then prototyping. This is where we stop at the moment, but in the future we really seek to go into serial application together with our parent company MTU. We are a team of 35 experts, constantly growing. We seek to be above 40 by the end of the year, and slowly building up an organization ready for the hurdles in aviation. Which also not often, if you're coming from automotive and from motorsports, not too easy often. Let me show you a few of the technology highlights. Firstly, I don't want to talk about in detail about our boost drive air. That's a technology which is a small actuator, which is currently being used in automotive. We seek to place that in aviation, but that's not the focus for today. I would like to focus on our main propulsion system, which is the boost drive speed. The boost drive speed is actually quite unique in terms of economic, but also technical reasons. Firstly, we've understood what the crucial topics in aviation are ever since we've worked together with MTU, and respectively we know what it means to design to cost, to design to production cost, to design to MRO, to design to maintainability. That's a key part where we say we've incorporated this from the very beginning of the engineering work. Secondly, we really seek to increase on the technical side, combine inverter and motor, so we have a very space-saving and very lightweight motor. We'll come back on the weight later. Yeah, on the technical side, of course, if we talk about power output, we always talk about continuous power output, and we do not want to brag with numbers here, but I guess we have a very leading power density at the moment. Second, we see very versatile application, so the motor itself and the magnetic circuit is patented, but the nice thing is we can design that to customer needs. So whether you need high speed or low speed rotation, whether you need an outrunner or an in-runner, that really depends on the client's needs, and we can adapt this based on the magnetic circuit technology behind. Actually, across all applications, we've seen above 96% efficiency, which has not only been simulated, but also verified for all the motors we have built on the test bench so far. And something we also would like to point out is, again, we understand aviation, we really design to certification, achievability, which is, I guess, something which should not be neglected. We've understood that, and we have some interesting technical things I'll come to later where we address this topic. I've said we place ourselves with a very high power density. At the moment, we're speaking of 15 kilowatts per kilogram across all three, let's say, motor models we have built with clients so far. We initially kicked off with 125 for motorsports, then continued to 250 for motorsports, and today, let's say our flagship model is a 600 kilowatt electric motor at the weight of 40 kilograms. So I guess any one of us here on stage could actually lift that thing with almost close to 1,000 shaft horsepower. For our latest application, we are running together with MTU, also on a fuel cell project actually. So that's the thing. As I said, 600 kilowatt continuous. That's quite important. So that's not peak, but we can really deliver that. The motor is designed for a classical flight profile. So we know what the flight profile shall look like, and respectively, we estimate 20 minutes of takeoff, full power, then into cruise, and then all the safety left for the motor itself to get down to the ground. We operate at a quite high RPM here, with 15,000 RPM, respectively. Need a gearbox here, which is something we do with partners. No. Of course, if we talk about cooling, this data is liquid fluid cooled, and as well as the rotor. We didn't do this rotor cooling with motorsport because it simply wasn't necessary. In motorsport, you go full throttle for a few seconds, then you leave off the gas, and in different requirement in aviation, which we designed the motor specifically for. The nice thing also is, you scaled that from 125 to 250 to 600, and we actually also seek to go further. We have already studies from 1 megawatt and 2 megawatt, and respectively we want to move beyond the urban air mobility and really move into the substantial regional aviation market. Let me also confirm that these are not only theoretical numbers. We've confirmed all this on the test bench. The current maturity level is continuously progressing. We are seeking to do system ground tests together with the fuel cell system next year, and then seek to really timely enter into production, not production, but product R&D, and push the whole thing further. Yeah. Basically some technical numbers confirming what I've just said. I guess I would again like to highlight that we have a very strong efficiency here. I guess we're talking about battery efficiency. The better the motor efficiency, the better for the whole propulsion system. I guess that's also one of our main targets, which we designed this engine for. You may ask, okay, why do we deem 15 kilowatts per kilogram industry leading, and what are we doing to realize that? One of the things, and maybe let me start from the right, highly integrated inverter. You can visit us at our booth, also here in hall A7. You might see it's directly attached. Yeah, you save space, you have no dedicated separate box. You reduce losses. So that's really the first thing where we say this has to be a key technology driver. Second, on cooling, we really rely on a quite innovative cooling method, increasing both the cooling surface as well as reducing the path for the heat to be dissipated. Thirdly, the winding technology. I guess that's also something where we see a lot of automotive technologies trying to drop into aviation, which we deem not ideal. To say so, we have developed something where we're working with layers actually, and really seek to, but we did increase copper fill factor dramatically and have a very successful results here. And finally, that's also something quite interesting. We all think about 3-phase motors, maybe 6-phase motors. We really try to increase that, so we're beyond 6. And additionally, we're not thinking as 6 phases for one motor, but actually in 2 hemispheres. So really to address redundancy, so if one of these phases basically breaks out. We do not have a complete engine failure, but with adequate software, we can downgrade the motor per rata and basically ensure a continuous flight performance. So, just to brag again, we have a very nice test bench which can do all that, which is part of our nice, small and nice setup. Actually quite impressive. I mean, this motor and everything which you can see here, we compromise in our small design of like 30 centimeters diameter and 40 kilograms. So you see what it takes on the other side to really handle that thing on a ground. We believe in partnerships. As said, we are part of MTU. Let me also highlight maybe our collaboration with AES, a company which is also a 50-50 joint venture between Safran and MTU. We're focusing on FADEX, so controllers, hard and software. We are working closely with them on the electronics and on the software side. So really, we think that it's, I guess David mentioned it before, you cannot do everything on your own, and you have to rely on partners if you want to go into aviation. So that's respectively why we have a quite broad network. If you would like to join, please find us in A7 or afterwards. Many thanks.
Okay, thank you very much. And so we heard now a lot about engines, about batteries. So now, in the end, we will have something about flying, as we are at the AERO here, and something about flying electric. Klaus has been here also several times. He was flying electric, he was flying records with electric, and so Klaus, stage is yours.
It works? Yes. So thank you very much. I'm just a stupid pilot. We saw a lot of technology which have some projection in the future. I'm more in the case what I have, what can I do with. And so my name is Klaus Ohlmann. I have 76 world records, 52 in gliding, playing around with renewable energies. And the rest is some solar records and electric world records. So I try always to find new partners and to show what they can do with their projective things. So just to show you a little bit in which I'm working, so a little video that show you some images with a scientific project from the DLR in southern Patagonia. You see the enormous energy of the wind there. Sunshine, wind is the other things that I would like to rose 13.5 meters per second. You see the energy that is in the air. This is in the area of southern Patagonia on the Argentinian side. And this is a Stemme aircraft which has a Rotax engine behind. And so we flew down from Santiago de Chile down to the south of Patagonia with a motor glider, and half of the flight was certainly with the energy of the air. It's around about 7,000 meters high here, and of course we use oxygen as well. So what is the goal for me? The goal for me is to show a little bit what we can do nowadays with some projections of the future, as well as all the people that are sitting here. What's going on? Okay. So this is the Stemme glider, and of course you know, or everybody knows, that gliders have the most of the efficiency of all aircrafts. due to their long wings, due to the aerodynamic design. So the Stemme, as I told you, has a Rotax engine with a propeller in front, and it's a very nice motor glider, not the best glider, but a very good compromise. So the idea was when I flew some prototypes, especially the prototype of the e-Genius from the University of Stuttgart, Institut für Flugzeugbau. And as I told you, I'm only the stupid pilot, and I have a lot of engineering friends. And so I'm a black box man, and I ask always the engineer, could you please make a little bit light in my black box to understand a little bit more how it works? And they succeeded. So I want to transfer, or we are transferring the very nice, efficient airframe from the Stemme glider in electric plane, because everybody knows electric motors have the highest efficiency of all motors that we know. And together with an airframe, which is a high efficiency, and all the other things, it would be very nice to transform it. So I have nice friends. In the middle you see Karl, which is our chief engineer. He has a background of more than 40 years with General Aviation, General Electrics and other companies. And he's really the guy from the mechatronics that I needed. I found him on an electric symposium, a little bit like here. He made a presentation, and I said, wow, this is the guy I need for my vision, because I want to promote electric flight, because we are handling all the day long renewable energy, but I was always, I did not find so nice that we always use this dirt under the fingernail with these fossil fuels for even only 3 minutes, but just to make zero emission, it would be nice to have electric flight together with a glider. So you see the team of young students and the professor from the University of Trier, and so they helped a lot. It's due to the network of my friend Karl, engineer. You see a little bit the powertrain that we will install, or is installed now in the Stemme. So you see the electric motor on the right hand side. It's a dual winding system, so you have a redundant system like 2 electric motors in one motor case. You see as well 2 electronics, the e-drive 500 and a second one inverter, which allows us, if any electronic fails, you have the chance to have 50% of power, which is enough for a glider to stay in the air and to make a safe landing somewhere. You see the battery in the middle, of course, and the controller, and the BMI battery management system, BMS, sorry. And then what we know nowadays, batteries are really limited, and I'm very happy to see all these people who make us promises, and I hope that they will hold it next year, or perhaps 1 year later. So my Stemme is a little bit a copy of the e-Genius from, it's a technological carrier. We use the electric motor, which will be quite fine, and there will be not a lot of progress with this system, but when we have new batteries, when we have other motorization, when we have probably fuel cells that could be integrated in this glider, because there's a lot of space where the former Rotax was. So I want to fly long range. We know the batteries, at least as I see, we cannot cross the Atlantic Ocean, or we need some trailer behind the glider or auto glider with batteries, and that will be a little bit difficult. So what we need a hybrid system, absolutely. And so we have a small industrial engine, because the start needs a lot of power, and we have a heavy motor for all this power that we need. And this is a small industrial engine, which is absolutely good enough to make convenient speed with this motor glider. So Vanguard, it's a Briggs & Stratton, there's in fireworker pumps and so on. It's a very solid engine, 1,000 hours and no oil consumption, and between 5 and 6 liters the consumption, and we hope to fly with 180 kilometers per hour with this thing. So just for your information, the normal Stemme, when I flew down from Berlin to Kathmandu in 2 weeks, we need round about 20 liters of fuel, or not gas oil, so with this motor, probably the same speed, we need only 6 liters per hour. That will say our range is much more important. And so what we can see a little bit here, there's a new design. We have in front the electric motor and the electronics right inside, a redundant system. And this is the cage, the frame that we have behind, where before the Rotax was in, and you see at the left-hand side, you see the battery systems, and on the right-hand side, you see the range extender as well with redundant systems. So I have only one range extender, so hopefully the promises of the engineers are okay, that but I have a certain redundancy, a little raft with me, and invest in order to survive in the Atlantic Ocean, because with this plane, you see the new design with the prop in front. It's like a conventional motor plane. In the future, it will be a folding system along the fuselage from the propeller in order to have as well a nice glider, which is nowadays. So what is the idea? Very long-range electric flights. For example, we have an idea to make a flight along the Silk Road. Of course, when you want to fly in China, you need some political aspects. I'm an opportunist for this case, and it would be very nice along the Silk Road, the old Silk Road, to fly and to make a story around that. The range, 3,000 kilometers. Actually, it's 1,500, so 2 times more range. So the idea is to promote electric flight, to promote less carbon exposure, and to make great stories with fantastic pictures. So if ever there are sponsors, you're welcome, or if you want to test your new batteries, you're welcome with us, because of course I will fly as well in pure electric, making some story around that, what to do, and to tell, okay, when we want to cross the Atlantic Ocean, we need the range extender. Probably we have some e-fuels in the future, and to make the carbon print much more less in aviation. I think we need that in aviation because we have a bad reputation for whichever reason, because we have so much fun in our planes. Thank you so much.
Thank you, Klaus. And yeah, this gives us also, especially here where we are a lot of pilots, the idea back again why we're doing all this, to keep on flying, also in times where there should be carbon reduction. So we have to do it, otherwise at some points maybe the people will shut us off, like they shut down airplanes because of airports because of noise, or they shut down whole aircraft or car classes because they say, like, there are inner cities where with some cars you can't go anymore, and there will be places also where with aircraft, when they are polluting, we will not be able to go. So this is why it's so important when we do it, and you give us the emotional impression which is connecting all this. We still have some time for some questions. I would have a question to the Theion company. As your batteries are quite, the technology is very different from the technology we are using now. When do you think we will have the first aircraft flying with it, so that we can see what are the values you can really achieve inside an aircraft in a package?
So, thanks for the question. asked this also myself quite often. So what we can do, so this year we will provide the first samples, small samples, that customers can really test, especially the conditions on high altitudes and also temperatures, vibrations and so on. Where I'm not an expert is what are the conditions that you can really fly from, let's say, safety perspective, and what conditions you have to fulfill. So my gut feeling tells me something like, with our technology, that it's really flying on a commercial base. We talk about 6 to 8 years.
Okay. Same question to David here with the Verdego. You mentioned that you're in some military project. You mentioned that there are some aircraft trying out the systems you developed. When do you think there will be the first available aircraft? Available means I, as a pilot, can buy the aircraft and go fly with the aircraft. So the first, probably the smallest system, this would be, I think, that the key question for all the pilots around here.
Yes, that's a very good question. We still have to get through certification, so that's from a realistic standpoint, that is a few years off. I would see these systems getting into aircraft that you can actually fly probably in the 4 to 5 year time frame.
Okay, just totally forgot, because I always have these questions and I don't think on my visitors in the show. If anybody of you has a question, please raise your hand and we'll get you a microphone so that you can ask the question while we're doing this. Question to Karl. Why did you choose the ultralight way for the first test vehicle? Because there, on a way, you're limited in weight, but what are the advantages to use this? I think it's a German ultralight category. You're at the moment having the first test vehicle flying in.
Yes, for us this was just a simplicity of certification requirements. When you work on such a system in the EASA regulations, the requirements are much higher. For ultralight certification, the requirements are lower. And for companies of the size like PSI-Tech and Kasero, the approach to go directly into a system in the EASA world would not have been reasonable. Yeah.
Okay, a same question now to you, back from the point of view, when can I fly the Dornier seaplane with a fuel cell and the electric motor?
Sometime this year.
So you're flying sometime this year, but when can I fly it?
You want to buy it?
No, just want to fly it at the moment, because I don't have a lake at home, and you know that seaplane flying in Germany is a bit difficult to get permission. Okay, you could also fly it on the wheels, but then probably you don't buy a seaplane.
You can fly as our guest in the experimental phase sometime this year, yeah.
Oh.
But for buying it, you must wait some more years, maybe in the same range as the Verdego systems.
Okay, so it will not offer the manufacturer, your cooperation partner Dornier, they will not implement it in a product right away. They will just try to get the experience.
No, the aircraft that you see now is first-hand only a test bed.
Okay, good. Another question to Professor Zhang from MontaVista. Do you already have batteries flying in vehicles, and what is the energy density of this batteries which is flying right? Because I think you have some, probably because of confidentiality, you can tell us where it is flying, but I would be interested, what is the density of those battery cells in the package level which are in operation right now?
The operation is already test operation, not really commercial. One is a solar powered airplane. We have in work with customers since the start, like 2019. They start test our cell. Now they are start to test to fly using our cell and the pack. For that purpose, we typically provide energy density from 400 to 500 watt-hour kilogram. It depends on what's the requirement for the cycle life. Some customers need a longer cycle life. We can have for 400, we can have up to 5 cycles, but for 530 watt-hour, maybe only 150 cycles. So it totally depends on what you use.
Yeah.
For drones, like small drones, actually, we typically provide 400 watt-hour per kilogram.
Yeah, I think, and I learned from technician talking with me that one of the key questions is also how fast you want to drain the battery. So how fast you need, especially at the VTOL, the takeoff phase. So one question to Theion at this point. I heard that you explained that your type of battery would be happy to give in and out the energy very fast, which is a problem with some of the high energy density cells at the moment.
Yes, that's one of the benefits what the sulfur brings with it. So it likes the high C rates. It also likes quite a wide temperature range to cover. So, but you always have to consider not only the anode, only the cathode, also the anode. It must be a balanced system. So honestly, most of the limitations in our battery system was mostly on the anode side, what we had to solve, and not on the cathode side. But in general, sulfur really likes the high C rate.
Okay, and question to eMoSys. You said you're relatively new. Yeah, we don't have enough. We have too many people because I always invite so many people because I'm interested in all the different things that we even run out of microphones. And with the eMoSys system, do you already have, let's say, projects in our small aviation world? So because MTU is normally delivering motors in a different world. And in this small world, or you have interested customers who want to use the motors, and in which time frame you think your motors will get airborne?
Indeed, besides the big MTU project, we really seek to do third-party business, and that's why we're here. I guess we've been in the stealth mode for the last years. That's why we're seeking to increase our presence, and I'm certainly going to reach out to Mr. Ohlmann later. Maybe we can replace one of these electric engines and some of these inverters. No, just joking. So we seek to have a quick second, let's say, lighthouse project with a test flight, but I guess realistically, whenever can one of our guests here sit in a plane with our motor, I guess I would also refer to early 2030s with all that certification which has to take place before.
Okay, thank you. We have a question from the audience.
Hi, it's working great. So I have a question to Martin and Professor Zhang about the batteries. So in my experience, one of the critical cases for existing battery cells is high discharge current at low state of charge, which is where a lot of things that are currently on the market run into a bit of a wall. How do your systems compare to existing solutions for that particular operational point?
Number 2. Okay. Thanks for the question. So, as you said, this is one of the challenges to have a high C rate. So you need a lot of power when the battery is already nearly empty for landing or whatever. So, finally, you always have to design a battery for the use case, and this is one of the use cases. But there is not one battery in a plane. There are several batteries mixed to a module in a pack, and I think to cover this really completely, you have to design specific batteries for the landing, for the cruising, and for starting the cruising and the landing phase and combine them to a pack, and then you can solve this issue.
Okay, if you answer it. Just one thing, this is the last question. We will have a little bio break then, and then we will have the next session, which will be about flight training with electric aircraft, and we have some interesting things coming up there. So in about 5 minutes, after we stopped here, and then don't miss it, 2:45, there will be the E-Flight Award of this year. And this year we have 2 prizes, so if you don't stay for the next session, then definitely come back at 2:45 for the E-Flight Award.
Okay, thank you, Willi, for giving the last chance to me. Okay, I think the question is that what's the difference of a new system compared to the existing lithium-ion system? Actually, for us, our approach, since we are using most advanced Käser, the current lithium-ion system, so on that side, the discharge capability is very similar. On the anode side, we're using lithium metal. Lithium metal, actually, electrochemical conversion is a faster kinetic property is better than intercalation type, maybe more too specific, right? The graphite and this alloy type, like silicon, normally their charge rate cannot be very fast. I say very fast means for electrical aviation, we need like typically 5C for this e-vehicle or this drones. But for emergency case, some customers say 7C, some say 10C, even some require 15C. So it depends on the type of your airplanes. But that's extremely, actually, much like 10 times, almost 10 times larger discharge rate than our EV batteries. So I think our lithium metal on that, because our system have very low internal resistance. So the heat, not only capability you discharge, but also depend on how much heat you generate when you discharge at this high current. That if you give too much heat, you will trigger the explosion we call thermal runaway of your cell. So that actually at a high rate, temperature rise is very critical. Okay. Yeah, we have spent a lot of time working on that, right? Maybe it's more specific. I think my point is the new system, if you are not better on that performance than conventional system, then only higher density is useless, right?
Okay.
Thank you.
Thank you for this last question for this session. If you just stay for a quick photo, and then I just have to get the next speaker because he's not here yet, and then we start again with the next session on flight training. So you come together here.
Electric flying and eVTOL, just go to your browser, type e-flight-journal.com, click enter, and you'll arrive at our blog site of E-Flight Journal with all the latest news on electric and eVTOL flying around the world. If you want to read the PDF or printed version of the latest E-Flight Journal, click on the button next to the image on top. You arrive on a site where you see the latest version. You can flip through the pages in small or enlarge, and then you can read it on the screen on your cell phone or tablet, wherever you want. If you want to read the magazine offline, click on the link below the image. You'll arrive on our Yumpu reader site, where you can either then flip through the pages again and read the magazine, or download the paper. You can save it anywhere on your computer or cell phone and then read it whenever and wherever you want. If you want to read another issue of E-Flight Journal, just scroll down on the Yumpu site and you will see the older issues of the magazine. Just click on it. After you clicked on it, you can then download this other magazine or immediately read it in the reader again. Just flip through the pages and enjoy all the news on electric flying, from flight reports to government information and technical information on all details. If you like it, subscribe the magazine and you will receive the updates on a regular basis. Thanks and goodbye.